our topic for today is section 9.9, which is representational functions by power series. So we are analyzing that connection that we already started in 9.8, and that is that we have a function that represents the sum of the power series. And then we saw also that we can differentiate this, integrate, and then do all kinds of analysis. But generally our idea today is, and that's 9.9, to start from a power series and recognize the function that represents its sum. And then in next section 9.10, we'll find the general method how to get power series out of the function. When function is given, how to get a power series. So in order to do this, let's recall one very important power series in the geometric series. And that is the sum of x to the n equals 0 to infinity equals 1 over 1 minus x through if x is between negative 1 and 1. So that's the formula we developed in section 9.2, which is a geometric series. No matter what x is, this is always true that the ratio of your geometric series, this formula is true. Now, generally, almost the whole lecture today will play around this formula. We'll manipulate this formula then for the power series to get the other similar functions. So here is another example. So example, represent f of x equals 1 over 1 minus x using power series centered at c equals negative 1, which means in terms of powers of x plus 1. So here we have powers of x, we want powers of x plus 1. So how do we solve this? The idea is basically, you can ask, why would I do that? Isn't this the best way we can represent 1 over 1 minus x? It might be that we are working on a problem where actually your initial values are close to negative 1. So you want state of your process at 11 o'clock, not at 12. And that's why you need much more presentation in terms of x plus 1 than in terms of x. So that's really sometimes comes out of the nature of the problem we are working on. But to avoid this complexity of this, so here is the trick that we want to use. That x plus 1 that we want to appear in our result will give us make a substitution and call it z. So from there, basically, our x is equal to 1 minus z. So now we want 1 over 1 minus x, which is equal 1 over 1 minus z. No, x equals z minus 1. Z minus 1. So it is 1 over 2 minus z. So it doesn't look much more complicated, but it's much better to do representation in terms of z, and then when I'm done, I'll recall that z stands for x plus 1, and that's what we'll do. So here it is. How do I represent this 1 over 2 minus z using the presentation in the box? Crucial thing in the box, because x could be any power expression, but number 1 has to be there if I want to call it. So I'll divide by 2 up and down. And now I can use this boxed formula, but just of course, who stands for x? Z half stands for x. So geometric series in terms of z half. So what would that be? Of course, there is extra. I have 1/2. I'll pull it out. So it will be 1/2 sum and go 0 to infinity z half to here. So I use power series. This is true for every x between -1. So if x happens to be 0 or 2, it's true for there. But also, we have to recall that since z half played x, we know condition of validity, z half must be between -1 and 1. And basically we are done. Why? Because what can we do here? I can write it like this, 0 to infinity. I can split this 1 over 2 to the n, z to the n. But there is another half in front of it, so I'll distribute it back. 2 to the n plus 1 z to the n. And that's equal. Now I just recall that z stands for x plus 1. So it will be 1 over 2 to the n plus 1, x plus 1 to the n. But now what? It's not a z. We can write this as a negative multiplying by 2, less than z less than 2. Now that z is x plus 1 is less than 2, less than minus 2. When I subtract 1, I will get negative 3, less than x, less than 1. Here it is. So here is the interval validity. Here is the formula. By the way, what we are getting here is also, if you compare it with 9.8, what appeared here is interval of convergence. So if I analyze this series for interval of convergence, I would get this one. So here we started from validity and actually got interval of convergence as an inverse product. If you go backwards, you would get the same thing. So this is the main idea for today. So play with geometric series to get lots of nice and interesting results. Please just do math operations. So here is the next problem, number 12. It says represent f of x equals 4 over 3x plus 2 using power series centered at c equals 2. Is it 2? At c equals 2, yeah. So what happens if we do the same trick? Since we need actually x minus 2 terms. So if it's centered at c equals 2, that means using powers of x minus 2. So, as a minute ago, we say, okay, let z be that x minus 2 that we need for the final product. So then our function will look like this. 4 over 3x plus 2 equals 4 over 3 times x minus 2 plus 2. We don't want that. For z equals x minus 2. I want to represent the x in terms of z. So z plus 2 equals to x. So I get 3 times z plus 2 plus 2. So we traded. We wanted z to represent x minus 2, so I can solve for x. X is z plus 2. We plugged in instead of x. We plugged in z plus 2. So here's the expression in z terms. So what would that be? Is 4 over 3z plus b. And then what do we do? Again, we want to build that 1 here, so we divide by 8, so we get 1/2 over 1 plus 3z over 8. Alright, I'm happy with this 1, but I'm not happy with this plus, because I need minus if I want to call the formula. But then we have easy algebraic tricks. It's no plus. I will put a minus because I need it for the formula, and 1 minus is a part of the z expression. And then what do? So then we will say the following. This will be geometric series, the same one as hello. It will be the same geometric series as the one that we have in the box, so we will use it when this represents our x. So what would that be? 1/2 goes in front of it, so 1/2, and we have the sum, and it goes 0 to infinity, and then this expression will stand for x, but be careful, together with its minus. So that will be sum of what? Negative 3z over 8 to the n. And then the same way as before, we have what? That absolute value of negative 3z over 8. Or negative 3z over 8 should be between negative 1 and 1. And that's it. So now we just polish it. What would that be? It will be what? 1/2 sum n goes 0 to infinity, negative 1 to the n. So we have alternation, 3/8 to the n, and then z to the n, but z stands for x minus 2, so it will be x minus 2 to the n. And then let's see the interval of convergence, basically. I'll multiply by negative 8/3. What will that do? I'll get 8/3 here. I'll get negative 8/3 here. I z here, but multiplying by a negative flips your inequality. So I'll write a smaller number on the left. Negative 8 over 3 is less than x minus 2, less than 8 over 3. Now I add 2 to both expressions, so I get what? 14/3 here, and negative 2/3 here. And that's the final result. So as long as your x is between these two numbers, then your expression 4 over 3x plus 2 could be represented using this power series. Let me check my calculation. 14 minus 1 to the n box. Good. That's it. So as I said, we are playing with the same idea, just rearranging expression so that we can call this formula. So what do we do now? Number 14. This is not right. So number 14, just similar adjustment. G of x equals 4x minus 7 over 2x squared plus 3x minus 2. The way it looks, it's not even close to this. But then you remember our old trick. We can decompose this using partial fraction decomposition. So that means we'll write 4x, so partial fraction decomposition, the old trick. So 4x minus 7 over 2x squared plus 3x minus 2. I'll rush this, so it's x plus 2 times 2x minus 1. How do you factor this? Put it in calculator, see the 0. And then that is a over x plus 2 plus b over 2x minus 1. And then let's see how much are a and b, basically. Although I can already do the development and just wait for a and b to be done. But it doesn't matter, so how do we get that? Let's recall, when I multiply by x plus 2 to x minus 1, we get the following: 4x minus 7 equals a times 2x minus 1 plus b times x plus 2. So if I plug in x equals negative 2, I get negative 15 equals a times negative 5, so a is 3. If I put x to be 1/2, then I will get negative 5, because it's 2 minus 7, equals b times 5 halves. So I get b is negative 2. Let me check it. Yes, 3 and negative 2. So generally I know it's 3 over x plus 2 minus 2 over 2x minus 1. And then what happens, a good thing here is just they didn't specify any other center of development, so we'll just use c equals 0. So what do? We just represent each of them. So 3 over, I'll write 2 plus x first. And then what? Since I'd like to have plus 1 and not minus 1, I'll distribute this minus in the denominator. So I get plus 2 over 1 minus 2x. And then standard tricks. Here I divide by 2, so I get 3 halves over 1 minus negative x half. Because we need that minus to call the formula. And then we artificially made it there. This guy is perfectly good. And now we can call the formula. So it's 3 halves times sum negative x half to the n when n goes 0 to infinity, and plus 2 times sum 2x to the n when n goes 0 to infinity. Of course, if you want, we can polish this a little bit. That's not essential, but if you want, we can. What would that give us? Sum and get them together. So what would that give us? It would give us the following. This guy has negative 1 to the n that comes from here times 3 over 2 to the n plus 1. So x, they both have x to the n, so I get that together here. Once again, a minus 1 to the n, here it is. 2 to the n, and this 2 is 2 to the n plus 1, 3 is just a 1. Plus, here 2 to the n times 2 is 2 to the n plus 1. This is how it looks. And what else is needed? Of course, we need validity of this formula. So for which axis we can use it. So then we need actually to analyze both of them individually and then see where they both belong. Because if you want this to exist, both things must exist. So here it is. We use this formula on negative x half. So we have what? Absolute value of x half has to be less than 1. So these are conditions. So absolute value of x half has to be less than 1, and also absolute value of 2x has to be less than 1. So first one exists if what? If x is between 2 and negative 2, and this one exists if x is between negative 1 half and 1 half. So if you want to have both, which is necessary to have validity of your result, and this is their overlap, so x is between negative 1 half. That's actually because this guy has more troubles converging. So let's see if we got 3 times plus looks good between negative 1 half and half. And then a couple of other problems with a different idea where generally what? Even if you don't see power series, you can still use it to get development using other tricks. So not just basic algebra, but also using integration or differentiation. So here is the idea how we can use integration. So problem 22, find representation, power series representation of f of x equals ln of 1 minus x squared at c equals 0. So what can we do? We need a couple of skillful tricks here, because I know that 1 over 1 minus x is the sum from 0 to infinity x to the n as long as x is between negative 1 and 1. Basically, I'd like to get this guy integrating, like, the whole idea comes from this integral of 1 over x dx is an absolute value of x plus c. So I'd like to integrate something like this in order to get ln. Maybe that's why instead of x, I should put x squared on both sides. But then that integral would not be correct. So here's what we'll do. We need to do 2 tricks at the same time. I will put x to be equal to x squared. If you don't like that, how can x be x squared? Actually, I multiply, I replace x to be z squared, but then I call it z. So 1 over 1 minus x squared is sum, and goes 0 to infinity, x to the 2n. So I replaced the x with x squared, and it's valid as long as x is between negative. So this is for sure correct. But as I said, this will not give me the ln that I need as integral, so I'll multiply both sides by x. So multiply by x. So what do we get? X over 1 minus x squared is sum n goes 0 to infinity x to the 2n plus 1, because everybody gets an extra x. What now? I will integrate both sides with an interval of convergence. Integrate. So what will that give me? Integral of x over 1 minus x squared dx equals integral of the sum n goes 0 to infinity x to the 2n plus 1. So as I said, if you are within interval of convergence, which is between negative 1 and 1, you can integrate the sum member by member. Now, so right side is much easier to integrate formally. What would that be? Sum n goes 0 to infinity x to the 2n plus 2 over 2n plus 2. And plus c, of course. How do we integrate this? Let me do it on the side so that we don't burden the notation. So, integral of x over 1 minus x squared dx equals, you put u equals 1 minus x squared, so the du is negative 2x dx. Remember that way. So this is our package. So it's integral of negative 1/2 du, I got negative half, over u. And that's then what? Negative 1/2 ln absolute value. So this would be what? Negative 1/2 ln of 1 minus x squared. Why is it that I didn't put absolute value? Because x is between negative 1 and 1, so I don't need absolute value. Expression is always positive. So here it is, we got our representation. The only thing multiplied by negative 2 both sides. So here it is. I'll get ln of 1 minus x squared equals sum n goes 0 to infinity negative 2 over 2n plus 2 times x to the 2n plus 2 plus c. And that c is, I'm seeing it probably out on the screen. So that's our almost final result, but to get the final result we have to decide what is c, because that sum is a fixed function, not something that has c ambiguity. But then what do? I just plug in some convenient value. Let me plug in x to be 0. So what happens on the left side? I'll get ln 1. And here all the members, because first member is not x to the 0, it's x squared. X to the 4th and so on. Each of the members gives me 0 plus c. So since ln 1 is 0, I'll get 0 equals to c. So c is 0. So our final result actually is this one. So ln of 1 minus x squared is equal to this sum. And what is the validity? For all x's that are between negative 1 and 1. Why is that so nice? Because now, whenever you need to approximate ln of 1 minus x squared for those values of x, you can use this power series and then cut it off somewhere. But generally, when you cut it off, what you are really getting is the Taylor polynomial. So generally, this topic is very similar to that topic of Taylor polynomial, and their full connection will be made in our section 9.10. Let's do one more really famous example where this is being used, and that is, let's use the same idea, the way it was very important, the way it was used in the history of mathematics, and that is, we want to analyze the following series. So here's the next example. We want to use, actually we'll not ask the question. Can we represent 1 over 1 plus x squared? So we'll use the same idea to show you the following very powerful trick. 1 over 1 plus x squared, so let me raise it maximum, so let me write again. Sum of x to the n when n goes 0 to infinity equals 1 over 1 minus x if x is between negative 1 and 1. So generally I want to use this, but generally I have to use it as 1 minus negative x squared. Now when I feed negative x squared for x into this formula, I'll get sum n goes 0 to infinity negative x squared. It's all valid if x is between negative 1 and 1. All right, so what do we do here? We will get that this is sum n goes 0 to infinity, negative 1 to the n, x to the 2n. But now what we'll do, we will integrate both sides. And when we integrate, here's what happens. We're integrating the sum. So what would that give us? Integral 1 over 1 plus x squared, we know that that's arc 10x. Equals. Now we will integrate member by members. People say n goes 0 to infinity, negative 1 to the n, integral of x to the 2n dx. So this will give us that arc 10 of x equals. We can put its sum n goes 0 to infinity, negative 1 to the n, x to the 2n plus 1 over 2n plus 1, and then plus c. So we are really doing the same thing as a minute ago, but even goes easier and nicer. So, and then we have to fix c, so plug in x equals 0. So we get arc 10, 0 equals, the lowest power is 1, so all of the powers have 0. Powers of 0, so we get 0 plus c. So the same way as a minute ago, we get that c equals 0, so we get the following. Arc 10 of x equals sum, and it goes 0 to infinity, negative 1 to the n, x to the 2n plus 1 over 2n plus 1. But then what happens? And this is all valid if x is between negative 1 and 1. That's what we are seeing to go with this procedure. But it happened because the denominator showed up in the process. Actually, sometimes after the integration, you might extend your radius of interval of convergence, and actually this converges even at 1 because you get alternating series. So it converges even at 1, and it also converges at negative 1. So it converges, so it got, now we just extended our radius of convergence. Why is that important? Because that's how first time it was used. Actually, so plug x equals 1. So we get the following, arc 10 of 1 equals sum, and goes 0 to infinity, negative 1 to the n, 1 to the 2n plus 1 over 2n plus 1. Since this is 1, but arc 10 of 1 is pi over 4, because the 10 of pi over 4 is 1. So arc 10 of 1 is pi over 4. So we get actually the following, that pi over 4 is the sum, and it goes 0 to infinity, negative 1 over n over 2n plus 1. And this is actually first time in the history of mathematics people were able to calculate pi. So it's 4 sums n goes 0 to infinity, negative 1 to the n, over 2n plus 1. Because I don't know if you ever kind of wondered, people talk very often colloquially about there are infinitely many digits because it's a transcendental, it's irrational, even transcendental, a real number, but then probably the dilemma is how is it that they get pi so precisely to thousands and thousands of digits. Actually here it is, calculus is doing it, not geometry, because now you can estimate pi as this sum. Of course you cannot take infinitely many, but if you take 1,000 then you will get a certain error. Generally, what is the problem with this formula? However spectacular it is to have it, this formula is not the best one because it converges very slowly. And if we recall what we know from alternative series test, if I cut it at n equals 1,000, so if I just take first 1,000 members, then the error will be in the order of the first omitted member, which is 1 over 2,001. So I need to add 1,000 numbers only to get 3.14, 15, so maybe 1 or something like this. So that's a very slowly converging process. If you look at the notes, you can see one very intelligent identity that Mahin discovered 100 years ago, and actually the one where you actually don't plug in, because we have to plug in 1, which is on the border of convergence, so that's why it goes so slowly. He was able to use some identity where the input are much deeper, and then when you plug them in, you also get powers of small numbers that make it converge very fast, and that's really good for practical purposes. This is theoretically important as the first way to calculate pi. If you use Mahin identity, you can see first 5, 6 members will give you 10-digit preciseness. So that's much better. You can just read it from the notes. I'm not going to repeat it here. What we'll do here now, we'll just see a couple of things. First, how to really get value of pi using this. A little more of that topic, how to use calculators to represent sequences and series. So we'll talk about this one, but in general about convergence on the calculator as well. We will now analyze the way to use a graphing calculator to represent sequences. So the first thing to do is to adjust the mode. So here is the mode button, and I already pressed the mode button, and then on this 4th line you have options for functional mode, which is the one that we used before, then parametric and polar, what we'll use in chapter 10, and sequential. So I will go to sequential mode. Here, whoops, didn't work well. Sorry, here it is. So I'm going to mode, and then I'll go here sequential, and I'll press enter. So now it's in sequential mode. So what will that do? When I press y equals button, then instead of offering me function f of x, it will offer me to enter the sequence. So how do I enter the sequence? So here it is. I will enter the sequence as 1 over n. And then it says, what's n minimum? So starts at 1, value at minimum, let it be 1. So I want to see what I did. So I better adjust the window. So it says n minimum is from 1 to 10. X goes between 0 and 10, probably, if I want to see them all. And then what about y? I don't need negative y's, and my values will not be too big, so let me say between 1 and 0 and 3. So if I graph this, here is, do you see these dots? So generally these are the members of the individual sequence. So these members basically approach 0, and I'm not surprised. But now I want to define difference. So this is just sequences. This is what we studied in section 9.1. But now I want to define a series. If you remember, series goes cumulatively. So here's what I'll do. I'll go V, and the V is yellow here, so this is V, my second one. So I'll go n minus 1 plus 1 over n. So what did I do here basically? I said the following. Start with 1, and then each time, and that's Sn. So cumulatively, this is my Sn actually. Whatever you accumulated in first n minus 1 steps plus 1 over n. So what is this doing? This is really producing harmonic series. 1 plus 1/2 plus 1/3 next time, 1/4. So this does cumulative representation. What is the value at the minimum? The value is 1. Let me graph now. So what happened here? That U sequence a minute ago approaches 0, but then V sequence cumulatively increases and increases. And you know, even if I go and represent like 100 members, when we go 100 members, it will increase to infinity, but slowly, because that's what we know about our harmonic series. So let me go here. If I graph here, here it is. You see how at 100 it's already getting bigger. So even if I increase window to make it less dramatic, so if y minimum is 10, y maximum is 10, when I graph it, you see how that actually behaves like ln, that sum, and goes to infinity. So generally, you see those individual members approach 0, but the sums go to infinity because members are just still too big, even if approaching 0. What can we do now? I can change my V and say V of n minus 1. Then I want each time to add, not n, but n squared. So what happens now? I'm really doing a hyper harmonic series. So that is 1 plus 1/2 plus 1/3 and so on. So what do I get here if I graph this now? Those 1 over n squared, if I want them to coincide, so 1 over n squared, or even faster, are going to 0. But look at my sum now. You see how convergent it is, and generally it converges. By the way, we estimated it somewhere. That sum is pi squared over 6, and we estimated it somewhere in our work to be using integral test. We had an estimate that is somewhere between 1.5 and 2, but that's actually nicely demonstrated here on the calculator. So it's individually goes to 0, cumulatively, which is the series. So as a sequence, individually, as a series, collectively. And then just one more example to illustrate what we just did a minute ago in that power series representation where we got pi. So what are we going to do? We'll go U of n minimum. So I don't want UN anymore. I'll just erase it. When you click on it, it gets erased. Vn is Vn minus 1. What do we add each time? We said we add, here is the member, -1 to Vn over 2n plus 1. So we say -1 to Vn over parentheses 2n plus 1. What's my starting value? When n equals 0, I'll get, my starting value is 1. But what is it that I forgot? Actually, my starting value is not 1, sorry, because we are multiplying by 4. So we want 4 times. So starting value is 4, and also I'm adding each time, I'm adding 4 times. I just wrote the second and third 4 times. So let me graph it now. What happened here? So generally first I better adjust my window. Let me adjust my window so that y goes between 0, y minimum is 0, y maximum is 4. And then let me see, how does it look now? And, or let me see how it looks. So v of n minimum is 4, and then we get 1 to the n over 1 plus 1. Good, looks like we typed what we wanted. Let me look at the window. 200. We go to 5, so strange. I got it by 1 bigger than what I wanted. So probably I entered something wrong with it, so let's see. So when n is 1, oh, the problem is, yes. So the starting value is not n equals 1, it's n equals 0. So here it is, I have to adjust it. So y equals n minimum is 0. Sorry, I forgot that, but yes. So u of n minimum is what? No, this is not u, v of n minimum is 4, and now let me see how will that work now. Much better. So here it is. I just didn't adjust the starting value because our start is 0, not at 1. So here are the values. So if I trace them, so here it is. If I go here, you have 328, 304, 305. So you see, alternating series always goes. Let me actually adjust the window again to be between y minimum to be between 3 and 4. When you graph it, here it is, look how it converges. So when I trace it, that's how alternating goes. One member is overestimate, one is underestimate. So here it is, 333 overestimate, 297, 283, 301, 325, 304. So it gets closer and closer. But look, it's really still far, as we said, because I'm taking only 100 members. So if I get closer to, like here's 50, so if I get closer to 100 member, then the 3.14 fairness value shows up quite close. So you see, I'm between 315 and 313. So lower value goes up, upper value goes down, and they kind of squeeze the result, and that's our number pi. As I said, lots of calculations needed, but I hope you got an idea how you can represent these processes on the graphing calculator.